Welcome back to another edition of Stat 568 Design and Analysis of Experiments. Today what we'll be doing is going a little bit further into multi-factor designs. Last time we just looked at the complete randomized block design, and it was great. But now we're going to go a little bit further, looking at not one-way, but two-way ANOVA. And we'll be looking at the Latin square, which will be a really interesting way to efficiently test a treatment with multiple blocking factors. So let's go take a look at that.
And we're back with another lecture of Stat 568 Design and Analysis of Experiments. Today what we'll be talking about are more multi-factor experimental designs. So last time we did the complete randomized block design. We showed how that's related to a paired two-sample test. And we also looked at the Tukey 1 degree of freedom test for testing for specific interactions between a block factor and a treatment factor. Well, today what we'll be doing is looking at two-way ANOVA, which is going to allow us to have more than one treatment in our design. And then we'll go into other special ways of doing blocking, specifically the Latin and the Greco-Latin square designs, which give us very specific ways to arrange factors, both treatment and block factors, in a design very carefully, with, again, the main goal of minimizing the amount of the sample size, right? And the amount of energy and cost and everything that it requires to run such a design. So let's get into that. Right, so today, the first thing we're going to talk about is the, I have two-way layout, or the two-way ANOVA, as in contrast to what we discussed in the first chapter, which was one-way ANOVA. So this is really not going to look that much different than what we did with the the complete randomized block design last time, except that now we're going to include an interaction term, because we might have two treatments. Say we have two different medications for blood pressure, and we want to know, one, how they each independently affect the subjects, but also, do they have an interaction? And in this case, unlike the blocking case, we're assuming, or we're considering, that there may be a non-trivial interaction between our treatments. And it makes sense, whether it's taking two different medications at once, applying two different additives to soil to help plants grow. Oftentimes when you apply two things together, there's a chance they're going to interact. So let's talk about that. Well, first, just to recall, recall that, we recall one-way ANOVA, which in my notes, I wrote in the form Yij is going to be mu, the global mean, plus tau I, the ith treatment effect, plus epsilon ij. So here we would have our global mean. We would have our ith treatment effect, and our ijth random noise, which, as always in this course, we'll assume is going to be normal with some unknown variance. Again, not always the case in practice, but typically the way we will proceed in this course. Okay, so we have that. Well, when we move into the idea of two-way ANOVA, now I'm going to change the notation slightly. And in this case, we're going to just throw a whole bunch more Greek letters in there, because you got to love the Greek letters in experimental design. So we're going to use IJL. So now we have a triple index for, basically, it's going to be treatment, let's say, factor A at level I, factor B at level J, and the replication, because we have to replicate now to be able to test for an interaction, replicate L. So I'll write that all out, and then it'll maybe make a little bit clearer. So we're going to have an alpha I, we're going to have a beta j, we're going to have a gamma ij, that's the interaction bit, and then we're going to have an epsilon ijl. So again, we have here, going through all the terms, we have our global mean, we have our ith effect for, we'll say, factor A. For beta, it's going to be the jth effect for factor B. So again, you can think of factors A and B as, say, maybe the dosages of a certain medicine or the amount of additives put into the soil if you're studying agriculture. And in this case, I is just going to tell us what level that factor is at. Is it, say, low dosage or 0, low, medium, high, for example? We're also going to have our gamma in here, which is going to be the ijth, I'm going to say A cross B interaction. In the other notes, sometimes, I should say, maybe in blue, just to keep with the multicolor scheme here, I'll say sometimes gamma ij, we might write that, as I did in a previous lecture, as alpha beta ij. And that's just to emphasize that it's the interaction between alpha and beta, but it's not strictly that I'm multiplying those two things together. It's actually a separate term that has, I guess, I cross j, or I guess if they're k levels, then it's some number of different levels that it can achieve as a factor. It's not strictly multiplication. I'll say sometimes write it as that. And then, of course, we have, once again, I'll just write the arrow in from up here, our random noise. This is for replicate L. Right, so to keep things a little bit simpler, what we can do is we can assume that we replicate every treatment the same number of times. What that means is, for a specific level of factor A and a specific level for factor B, we're going to replicate it the same number of times. I think in my notes I was using probably little n. Yeah, little n as the number of replicates. So here we have, I'll say, with I going from 1 to Ka, which is the number of levels in factor A, with J going from 1 to KB, the number of levels in factor B, and L going from 1 to N, where this is the number of replicates per treatment. And remember, the treatment in this case is the combination of the experimental factors. So a specific value for I and a specific value for J is kind of the treatment. So for every combination, every combination of I and J, we're going to have N replicates. I always have to make sure I say replicate and not replicant, because that's a slightly different thing if you're a Blade Runner fan. Not the same as experimental design, but still kind of a neat idea, I guess, science fiction wise. Anyway, yeah, so we have all of this. Again, one thing just to note, this is mathematically the same as replicating ACRBD, the complete randomized block design from the previous lecture. But typically, a block is something like, let's say, age range, or other things like that, or I don't know, I'm trying to think what else could be a good blocking factor. I guess age range, let's say sex, let's say a person's weight. It would have to be a weight category, because you could use a person's actual weight as a covariate, and we'll talk about that when we do ANOVA, which is analysis of variance with covariates. But any sort of categorical or ordinal categorical variable that typically is not something that we're testing or we're applying to the subject, but something that's kind of just already there, would be our blocks. Meanwhile, right, and again, I should say where we typically assume no block treatment interaction. And okay, that could not necessarily be true, right? You could have, say, your blood pressure medication, which may affect the elderly more than young people, or vice versa. But really what the block is doing is saying that, let's say on average, I'm just going to make this up because I don't really know the biology, but we'll say as people get older, maybe their blood pressure gets higher on average. So, or maybe there's a higher variance in their blood pressure and we have to account for that. So by blocking based on age category, you control for that. And as I mentioned in the last class, we typically would just make the assumption that there isn't going to be an interaction there between the block and the treatment. Of course, oftentimes there actually may be, and in that case, we could replicate it. And if we were to replicate such an experiment, complete randomized block design, we'd really have mathematically the same thing as a two-way layout, where we'd be able to have an interaction term in our model. And yeah, when we, so that's just a little side note. We'll block that off. Now, when we consider this such a model, let me write it again because it's now fallen off the top of the page. We have something, my OneNote will stop jumping around. Just to write it out again, we have something that looks like mu alpha I, beta j, the interaction term gamma ij, and epsilon I j L for the noise. Now, once again, what we do is we do a sum of squares decomposition, and the sum of squares decomposition is going to allow us to do our statistical hypothesis testing with the f-test. So in this case, our total sum of squares, we'll say SS tot, is going to just be it's going to be a triple sum. So we're going to need 3 sigmas here. Yeah, these things get kind of nasty looking after a while. We have I from 1 to Ka, we have J from 1 to Kb, and we have L from 1 to N, the number of replicates. And what we'd be doing is we'd be taking our IJLth observation, subtracting the global mean, which is going to have 3 dots now, saying that we're averaging over all 3 indices squared, and again skipping the tedious arithmetic, what we're going to end up with is an A sum of squares for factor A, B sum of squares for factor B, an interaction sum of squares, which I'll write as A cross B, and then finally an error sum of squares, or residual sum of squares for whatever's left over. So right, we have the actual equations for all of these. I will write them down just to make it, they're in my typed up notes, but it's kind of nice just to look at, just so we have them written down. Remember, when we do the A sum of squares, we're actually summing over all the J index, we're summing over J, and we're summing over L. And since factor A doesn't depend on J or L, it only depends on I, what we get is we get an N and a KB out front, and then we're summing over all I from 1 to KA, and what we're summing is just going to be YI dot dot, or bar dot dot minus y bar dot dot dot. And similarly for the other term, that is for the b sum of squares, it's going to look exactly the same, except I'm replacing a and b inside the equation, and I'm replacing, not an equal sign, I'm replacing the j or I index with a j index. And otherwise, nothing really has changed here, except the dot positions and whatnot. That's too many dots. We need 3 dots. All right. The interaction term now is going to be a little bit different because we didn't have this in the last design, so it's worth writing down. In this case, we're still summing over all of the replicates, so we still have an n out front. We're not, the summing over L doesn't change, doesn't have any effect but to just replicate or add this thing to itself n times. So now we're going to sum j from 1 to ka, and we're going to sum I from 1 to kb. And in this case, what we have is we have the ij dot. So we have the average of all the observations, such that with a specific I level for factor A, a j level for factor B, and we're averaging over all of the replicates. So this is why we need to replicate, because we need to be able to, in some sense, have a third index in our yij L in this case, so that we can average over L and keep ij fixed. And then we get this kind of peculiar thing here where what we do is we subtract the mean from I, we subtract the mean over with a fixed j, and then we actually end up adding back the global mean. Again, I'm not going to go through the actual derivation of this, but if you do it like we did in the previous lectures, you can kind of see where this comes from. Basically, throw away the squares and note that you have to add in, basically add up all the terms to make sure you get the thing for the total sum of squares on the left-hand side of this equation. I'll put star up here. Right, so we have that, and then we just have the air sum of squares, which is not too exciting. The air sum of squares in this case is just we're summing over all I, j, and L, and we're summing the usual thing, which, there's a bar in there that I need to remove, a typo in my notes. We're summing the ij Lth observation, and we're subtracting the category, the ijth interaction category mean. And yeah, that's what we get for our sum of squares decomposition. And I think if we were to put all of these back together, just doing it by eyesight really fast, yeah, it looks like everything should cancel out, because you have 2 yi bars, and you have a yi bar and a minus y bar I, and you have a y bar j and a minus y bar j, and so on. So anyway, the more interesting bit than actually writing this down is going to be their distribution under the null hypothesis, right, which is going to be chi-squared. So what I'll do over here is say that these, well, I'll say under H naught. Remember, I say under H naught or under the null hypothesis just as like a blanket statement, but what I mean by that is that each of these terms has their own null hypothesis. For factor A, it's that none of the levels of factor A have any different effect than any others. For factor B, it's none of the levels of factor B have any effect different than the others. And for the interaction, it would be that none of the interaction terms are different from any others, which if we assume the sum to 0 constraint, then we're just saying that none of the factor levels are different than 0, if we assume, again, sum to 0 as our constraint to make this mathematically make sense. Right. Anyway, under the null hypothesis for each of these terms respectively, we get chi-squared distributions, and the degrees of freedom are going to be important. Again, the way to think about it is often how many things do I have in each term, and how many things am I estimating? For the first one, I have I, and I runs from 1 to Ka. So I get a Ka here. But I have to subtract 1 for the global mean. And similarly, for this term, we have J from 1 to KB. So I have a KB here, but I have to subtract 1 for the global mean. For the interaction term now, things are, well, you kind of saw what it was in the complete randomized block design. It's actually going to be, I'll just write down the answer and then we'll talk about it in a second. It's going to be Ka minus 1, Kb minus 1, which, if we kind of write that, is going to equal Ka, Kb minus Ka minus Kb plus 1. So if we go back to the sum of squares equation on the left and the center here, what we have is we have Ka times Kb y bar I j's, which is a weird sentence to say out loud, but it's basically I have Ka times Kb of those terms. Then I have to subtract Ka of these, subtract Kb of those, but I get 1 back from the global mean. Again, it's not always the most satisfying thing to do to go about it in this way, but it allows us to kind of intuitively understand what's going on and not actually have to go through all of the linear algebra headache that would be to actually properly use Cochrane's theorem to determine the degrees of freedom. So that's those terms. And then the last one, which I'm going to write on the next line here, is our air sum of squares. This is the only one that doesn't require a null hypothesis. We always assume that the air sum of squares follows a chi-square distribution with a certain degrees of freedom. In this case, we have the total sample size, which is going to be n, Ka, Kb, and we're going to subtract the Ka times Kb group or category means that come into play here. So yeah, there's a lot of, again, the degrees of freedom are a very critical part of the course, and they're also can be quite confusing. So please talk to me in discussion times and office hours if you have questions about where some of these numbers are coming from. The one thing that's always good to check to make sure I didn't make a mistake is that if I were to say take all of these degrees of freedom and add them together, I should get the total sample size minus 1, which is the degrees of freedom for the total sum of squares. So let's just make sure that that actually works. If I take all of these terms, we'll write this as Ka, Kb minus Ka minus Kb plus 1. It's arithmetic, but it's annoying arithmetic, isn't it? N, Ka, Kb minus Ka, Kb. And then if we kind of work our way through this with my red, what we should get is, well, Ka here cancels out with this Ka, and this Kb cancels out with that Kb, and this minus 1 cancels out with that plus 1. This interaction term cancels out with this, and the only thing we have left is the total sample size and a minus 1. So that's basically the ranks of these respective matrices if we go back to what we learned about Cochrane's theorem, and how they all kind of add up nicely together. So, okay, we got what we wanted. That's good. And then from here, well, we basically just go forward and we say, now we can do F tests. So what I'll say is from here, we can do, I'll say global F tests for A, B, and A cross B. it is always good to remember that we are doing 3 hypothesis tests here. So we may need to consider multiple testing correction. This is only 3. It's not terribly large number, but it's still good to always be in that mindset, because as we go further in the course and we get to factorial designs, we could be doing 8 or 16 different hypothesis tests, and then we really need to account for multiple testing. So we'll put a side note. Consider multiple testing corrections, which we will do in a future lecture when we look at this more properly. But for now, I'll just say, for example, replace the test size alpha, which is kind of abusing or overloading the notation, with, let's say, alpha divided by 3, which is Bonferroni's method. If I can spell that correctly. Well, that's close enough. I always forget how many R's and F's and whatnot and N's are in Bonferroni. That doesn't quite look right. I think it's only 1 R. Doesn't really matter. We'll just end that parenthesis. So yeah, the point is that we are going to end up doing 3 different hypothesis tests. So it is worth considering that you are in a multiple testing scenario. The nice thing is that because I should say, given this setup, all hypothesis tests are independent, which is nice. Because it's not always the case. If you're just doing, say, linear regression and you have, say, 2 different independent variables and you want to consider the interaction of those independent variables, typically you're not going to have independent hypothesis tests, because the points, the data that you collected is just kind of whatever you get. But in an experimental design setting, we carefully consider all of the data points we have. We make sure that for every level of A, we test B, and for every level of B, we test A, and we test it the same number of times, in this case, N replicates. If we don't have the same number of replicates in each of the treatment categories, we're not going to have independent tests. Things will be a little bit, messier. So if possible, it's always good to have the same number of observations in each treatment category, like we set up in this setting, or like we designed this to be. Oh yes, and one more thing. You can then do a post-hoc Tukey test if the F-test rejects H naught. The last thing to point out is that you can do a post-hoc Tukey test in this case if you reject the respective F-test. So if you, for example, rejected the null hypothesis for factor A or B or the interaction term, you can then do a post-hoc Tukey test to compare the different categories. Now, it's important that I emphasize that you have to reject the F-test first. Last year, which would have been, I guess, 2020, I put a question like that on the midterm and said, what do we see from this? What can we learn from this Tukey test? And most people said, oh, well, we see there's a difference in these categories. And I said, no, the point is you can't learn anything because we didn't reject the initial F test. And if you don't reject the global test, you can't look for pairwise differences. It's like you're saying there are no significant differences here, so now we're going to go look for significant differences. Like, yeah, don't do that. Yeah, don't do that at all. Otherwise, yeah, you can just proceed as usual and do your post-hoc testing. So if you're reading along in my notes, I have a very small, like half page on random effects. I don't really like discussing the random effects in this setting, so I'm going to actually just skip that. In some sense, I should probably just delete it from my course notes because it's better reserved for other courses. But the next thing we need to do is discuss the Latin square design. Oh yeah, we got time to keep working on this. All right, so that's the end of our two-way ANOVA. Now let's consider Latin squares. Latin squares are one of these fun little mathematical objects, and even if you don't know what a Latin square is, I'm sure you actually have seen them before. They're Sudoku puzzles, for example. The Sudoku puzzle has an extra restriction, which is that you have to have every sub 3x3 square has to have all of the symbols appear once, but I'm getting ahead of myself. The idea of a Latin square is basically a k by k square with symbols, with, I think, k different symbols, such that each row and column only basically has one of each symbol. So, for example, I think the easiest one to do would just be a 3x3. And I say symbol because it could be anything. You could put numbers in there like you would in a Sudoku puzzle. It doesn't have to be numbers. It can be letters. It can be smiley face, star, frowny face if you really want. I'll use letters, and it would look, for example, something like this: ABC, BCA, CAB for the building that I currently am not allowed to go into because of COVID. And here what we have now is a 3x3 Latin square. But we could actually extend that to larger Latin squares, that is 4x4, 5x5, 6x6, even though that's a little bit of a weird one, which we'll talk about in a second. And the Latin square is going to allow us to have a very efficient way to test a treatment within two different blocks. Sometimes you could try to plug in more treatments, but again, we're not going to have enough, unless we replicate it, we're not going to be able to test for interaction. So the classic setup for the Latin square, why don't I just write this down rather than rambling out loud about it. The classic setup is sort of two block factors, one treatment factor, or experimental factor, if you want to call it that. And like literally this came from the idea of taking a big plot of land in agricultural research and cutting it up into little square plots. So you actually had the physical square sort of cut up on the ground. A lot of the stuff that we'll be discussing here comes from agricultural research and proper statistical designs for agricultural research. I always wonder when I'm driving down the street towards the university, or I should say up the street heading north, past the U Alberta farm campus, if they ever do anything like this at their setup. I don't actually know anyone in agriculture, so maybe I should go knock on their door, even though I guess nobody's in their office at the moment. Anyway, so let's do a 4x4 example to show you what I mean. And the idea is that we can have block factor 1, which is going to be something, this is going to be block 1. But I didn't give myself enough room, so let's just move this down ever so slightly. If my computer is willing. Excellent. And then what we'll do is we'll have a 1, 2, 3, 4, and this will be block 2. So we have two different block factors, and then we're going to have a single treatment factor, which I'm going to denote by A through D. And in this case, we can have, say, we'll change the color. Let's say A, B, C, and D. B, D, or B, A, D, and C. Let's see if I can do this right. C, D, A, and B. And lastly, the alphabet backwards, D, C, B, and A. So in this case, we would have sample size of 16 with, again, 2 block, I guess 3 factors. So we have 2 blocks, 1 treatment, and a sample size of 16. And this is quite neat because, if we did this as if doing a complete randomized block design, well, what we would want to do is we would want to see every level of the treatment within every block combination. I shouldn't put an arrow there because that's not a CRBD. If doing a complete randomized block design, we'd have basically, we'd have how many different block combinations were there? We would have 4 times 4 times 4, which in this case would be 64. So a much larger sample size. Because in the complete randomized block design, for every combination of block 1 and block 2, we would have to see all 4 treatments. In this case, not every possible combination of block 1, block 2, and the treatment occur. For example, if I know the level of block 1 and the level of block 2, only a single treatment is tested. But because of this nice setup, we have a lot of, elegant properties that we can use. And I actually have a pretty cool example of this that I used when collecting my own data, which maybe we'll talk about at the end of this course or this lecture. But for now, what you can imagine is it's a big plot of land and someone just cut it up into a 4x4 grid of 16 subplots. And then on each of them, they applied some factor level A, B, C, or D, which could be a different type of fertilizer, say, and we want to know how many plants grew or the size of the output of our plants in each of these squares would be one example. So the model that we end up with is going to look like something like Y, I, J, L again. But it's going to be a bit different than that 2-way layout that we did last time. We're going to have a mu. We're going to have an alpha I. We're going to have a beta J. I'm going to use those for the blocks, so I apologize that I'm kind of swapping my notation around, but these are going to be for the row and the column. And then we're going to have a tau L for the treatment, and then we're going to have an epsilon I J L for the noise. So once again, mu is always the global mean. I'm not going to write that again because I wrote that like 10 times already. This is going to be alpha I is the ith row effect. Beta J is going to be the jth column effect. And then tau L is going to be the lth treatment effect. And then, of course, noise, epsilon I J L. And just by noting, though, that not every index combination of I, J, and L exists. So it's a little bit different than the last time, and the sum of squares will kind of reflect that. So it's it's slightly more confusing, but what we end up with is we still get a nice sum of squares decomposition, which in this case is going to become the row sum of squares, the column sum of squares, and the treatment sum of squares, TRT for treat, and the air sum of squares. So in this case, we're going to have, a slightly different formulation and slightly different degrees of freedom. For the row sum of squares, what we do is we sum I from 1 to k of, and remember, in this case, one of the weird little subtleties of the Latin square is that all of the factors, block and treatment, all have to have the same number of levels, which make it a little bit cumbersome, I guess, or restrictive, maybe is the right word, a little bit restrictive in the sense that you actually have to have the same number of levels in each case. So yeah, there's a little bit of issues there because oftentimes you may not have the same number of levels for each factor. Anyway, yes, so for the row sum of squares, what we end up with is we end up actually with a k times the average over I minus y bar dot 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 squared. For the column sum of squares, we have, in some sense, the exact same thing, just switching I for j and moving my index 1 down. So dot j dot. That's not a double square. That's a 2, and that's a dot dot dot. We'll also have our, in this case, treatment sum of squares, which again is going to look exactly the same, except that j becomes L and the index moves 1 more down. And dot, dot, dot. And the last one, which is the error sum of squares. And this one becomes a little bit harder to write down explicitly because the summation is a bit weird. And in my notes, I just sort of said, we're summing over I, J, and L, but it's restrictive in the sense that if I have a specific value for I and J, there's only one possible value for L based on that above square that's running off the top of the screen. So in some sense, I'm only summing over, in this case, k squared, or in the case where k is equal to 4, 16 different terms in this sum, because we only have 16 or k squared observations, not k cubed. Like I said, degrees of freedom and the sum of squares start to get pretty complicated, but the Latin square is actually quite interesting, and I believe it shows up not just in agricultural research, but in things like marketing research and other places. So we'll have to investigate that further, because I believe I have there's some articles that discuss that for your review and article project. Okay, so I'm going to write this down again. I really don't want to go through the headache of trying to derive the whole thing because it's super annoying. But if you really wanted to, you can take the total sum of squares, you can decompose it into the specific sums of squares, and then you can work through it using something like Cochrane's theorem again. Now, in this case, each of these terms under their respective null hypotheses, again, always under the null hypothesis, because that's what we're doing. We're in frequentist statistics. All of these are going to have degrees of freedom k minus 1, which kind of makes sense because what it is it's saying I have k category means, and I have one global mean that I'm subtracting from that. So I have k minus 1. Now, then the question is, well, what in the world do I do with the degrees of freedom for this guy? Well, the easiest way to, there's actually, I guess there's two ways to do it. If you want to do the degrees of freedom using my little counting, shouldn't call it mine, just like it is just an easy counting method, then what you can do is look to see how many terms are in each of these, or how many unique values are in each of these terms. So the first one we would have is k squared because we have k squared observations. Then we would have k observations at k means, which is a whole nother thing. K category means for I, k category means for J, k category means for L, and then we can actually add a 2 on there at the end. So this kind of thing is going to be, well, k squared minus 3k plus 2. And if you remember factoring polynomials like you would have done in high school algebra class, presumably, then what you end up with is k minus 1, k minus 2 as our degrees of freedom for the air sum of squares. And once again, we can add these all together to make sure they actually work out. And sure enough, if I add k minus 1 plus k minus 1 plus k minus 1 plus this thing for the air sum of squares, I'll get exactly k squared minus 1, which is the degrees of freedom for the total sum of squares. All right. So we have that. And yeah, that means that that means that we can do our F test as usual. And the point is, so again, I kind of mentioned this before, but the main point is sort of efficiency. It's efficiency in the sense that we can test 3 factors with only k squared observations, not k cubed, which could be quite a big increase, right? Like going from 16 to 64 is a pretty big increase, and you may not have the budget or the ability to collect that much data in your experiment. I mean, if it's 10 by 10, right, you're going from 100 to 1,000, which is quite extreme, and gets worse from there. Yeah, so that's really the main thing. And once again, we must assume no interactions between any of the factors pairwise, or I'll say all 3 at once. So it's not just we need no pairwise interaction and no triple interaction. Typically, higher order interactions are very rare anyway, after you've considered the lower order interactions in the main terms. But it is something to remember that if there are interactions, they will affect the significance tests that you do. So again, we can use Tukey 1 degree of freedom if you want to look for an interaction, or replicate to test for interactions. Right, so those are the 2 different things you can do sort of going forward if you have this. I have an example of some agricultural data that I will look at, but I'm going to save that for the sort of third part of this lecture, because before I jump into that, what I would like to do is look at just discuss the Greco-Latin square, and then I think we'll stop here and do a little bit of R code just as an example. So the next thing to discuss is the Greco-Latin square. So the Greco-Latin square, this extends the Latin square to have 2 blocks and 2 treatments. Again, strictly speaking, they don't have to be 2 blocks and 2 treatments. You just have 4 different factors. But again, this is coming from the agricultural setting where, again, you're actually blocking by row and column within some actual plot of land that you're chopping up. Yeah, so that's the traditional setup would be 2 blocks and 2 treatments. It doesn't strictly have to be that way, but we still have to assume no interactions. So if you have 4 different treatments, you have to have a pretty strong assumption that none of them are interacting with each other, or you could run into some trouble. And this will actually come back again when we look at factorial designs and things like that. But okay, so what is a Greco-Latin square? So the rough idea, the idea is to combine 2 orthogonal, there's a good math word, orthogonal Latin squares. So if you're familiar with linear algebra, you know that the idea of orthogonality, right? You have 2 vectors are orthogonal to each other. It means they're at a right angle. And that notion is extended in various ways mathematically. Now, for the Latin square, you can actually have, so if you have one Latin square, you can permute the rows and the columns to get a new Latin square, but it would be equivalent to the first one because you're just flipping rows and columns around. If you can write down another Latin square that cannot be translated into the first one by row and column swaps, it's orthogonal. So in this case, that is, we'll say 2 Latin squares that cannot be transformed into one another via row and column swaps. I guess they would say row and column operations, I guess, but effectively you're just swapping them. So that's the way I like to think about it. So it's quite interesting because you either have a Latin square that is equivalent, and you can't have 2 equivalent Latin squares to combine, because if you combine 2 equivalent Latin squares, the factors actually overlap each other and you can't test for them independently. They confound, or they, I guess alias would be another term. They kind of overlap each other in that way. Whereas if you have them orthogonal to each other, you're actually testing the 2 treatment factors independently of each other, which is quite neat that you can cram an entire another factor into your k by k sample. So yeah, let's write that down. If we take the Latin square we had from above, which is going to be A, B, C, D, B, C, D, D, C, oops, A, D, C, D, C, A, B, B, and an A. All right, we got that one. So this would be the same Latin square I had above. Now, it's Latin because it's the Latin alphabet characters. Now, let's say we cross that. I'm not even sure if that's the right mathematical notation, so maybe I shouldn't do a cross, because the time sign with a cross in it is kind of a specific mathematical term. So we'll just put a comma there, and I can write down a Greco square, which will have the Greek letters alpha, beta, gamma, delta in it. So I can say alpha, beta, gamma, delta. These would be the 4 levels of a new treatment factor. Gamma, delta, oops, that's not a delta. Gamma, delta, alpha, beta, delta, gamma, beta, alpha. Yeah, swap those. Delta, gamma, beta, alpha. And lastly, beta, alpha, delta, gamma. Sounds like I'm sending out some sort of radio signal. Okay, so now that we have our 2 orthogonal Latin squares. So the claim is that you can't transform. So you could replace, say, the alpha, beta, gamma, delta with A, B, C, D. And then the claim that I make is that you can't permute the rows and columns of the first one to get to the first Latin square to get the form of the second Latin square. And if we combine them by actually just applying, say, factor level A alpha to the first one, and then B gamma to this one, and C delta to that one, and D, I guess, beta, and then so on. So I'm going to write this out. It's kind of, well, at least this one's not so bad. We'll say C gamma, D delta. And then we get what? A delta, D alpha, C beta, D, jumped on me again, D gamma, A beta, and B alpha. And lastly, we're going to have C alpha, B delta, almost there, guys, and A gamma. All right, so that looks kind of nasty, but the interesting thing about this square is that every combination of letters, Latin plus Greek, occurs exactly one time. So you can check that if you want, that if you pick any combination like C and delta, then there should be somewhere a single copy of C and delta in there. And similar to all of them, there should be no repeats. If there's a repeat, we did something wrong and we have to go back. And again, this is so this is just one way that you can now cram another factor into your model, assuming that there's no interactions. You're going to end up with, let's say, an SS row, an SS column. We'll say an SS maybe Latin for the Latin character, and a sum of squares for the, I'll say, GRK for the Greek characters. And all of these are going to have chi squared with k minus 1 degrees of freedom still. And now our air sum of squares is going to lose another k minus 1 degrees of freedom. And it's going to look something like, it's going to be k squared minus 4k plus, no, is it minus? No, plus 3. Yeah, plus 3, which, if we factor that, is going to be k minus 3, k minus 1. So a couple things to note. Well, first of all, you can't have k equal to 3, because then you're going to have 0 degrees of freedom for the air sum of squares. And it turns out that, there's only one equivalent class or of Latin square when you look at a 3x3. Going higher than that, you can do a 4x4 Greco-Latin square or 5x5. One little fun fact, I'll say fun fact, kind of an annoying fact actually. There are no Greco-Latin squares when k is equal to 6. So why? That's you have to ask a combinatorist and complain to them, because it has to do with factoring in a weird way. If k is a prime number or a power of a prime number, like 4 is 2 times 2, or 5 is prime, 7 is prime, 9 is 3 times 3. 16 is still good. That's 2 to the 4. So if you're a prime or you're a power of a prime, you're pretty much set because math said so. We're not going to get into that at the moment, but if you happen to know much about number theory and some of the theorems in that subject, that might make a little bit more sense as to why that's true. Otherwise, if you happen to have k being a composite number, which is the product of two or more distinct primes, sometimes you run into trouble, like not being able to find another unique or orthogonal Latin square. So if I write down a 6x6 Latin square, every other 6x6 Latin square can be achieved by row and column transforms on that original 6x6 one that I would write down. So again, there's other little headaches that will come into if you're trying to design an experiment like this. Lastly, I will also say these can be extended further to hyper Greco-Latin squares, which I'm not going to write down because it's going to be horrendously messy, where I'll say 3 or more orthogonal, mutually orthogonal Latin squares are combined. Right. So yeah, in certain cases, it just doesn't work. Like when k is equal to 6, math says, sorry, you can't do it. But if k is equal to 7, then you can actually have, I think, well, mathematically, we could work it out. I think you can have 6 different orthogonal Latin squares. So you can just keep cramming them together basically to create some giant hyper Greco-Latin square with lots of treatments all crammed into those, let's say 7x7 or 49 observations. Of course, there's always the problem that, again, we have to assume that there are no interactions happening here, or things will, fail in the sense that you might get some erroneous results because those interaction effects might bleed into the terms that you're testing, and you may get or miss significance where you otherwise should or should not have seen it, if that covers every single base in that sort of peculiar sentence. Right, so we're going to take a quick break. I'm going to go put something in the oven, and then I'm going to come back and we're going to do an example of Latin square in R just to give you an idea of what's going on. And I'll tell you a little bit about how I used the Latin square myself in a recent research project when I was collecting data back, I guess 2 summers ago now in 2019, when the heating was out or the air was out in our building and everything was horrendously oppressive. But that's a story for another day. We will be right back and we'll talk about that then. All right, and we are back with the last part of our lecture. So what we have done so far is looked at Way ANOVA and the Latin square and the Greco-Latin square design. What I'd like to do is show an example of the Latin square as it was used in agricultural research, and this data set is available in R, so you can download the package yourself and try it out yourself if you'd like to see this or more agricultural data sets. But first, actually, no, we'll do this first. This is probably the first thing we should do. So what we're going to do is look at the AgriDat library, or package, I should say, in R, which really just has hundreds of different experimental designs for agricultural data. The one we'll be looking at today is called Golden Latin, and this comes from a textbook on methods of statistical analysis. So the idea of this one is that we have a plot of land cut into 25 subplots. So it's a 5x5 Latin square. And the entire plot has wheat crops on it. I should move this up to the top so you can see. And the idea is that we want to test for how different treatments applied to each of the plots affects the growth of fungus, or testing the fungicidal properties of our different treatments. So here we have A through E. A is dusted before rains, B is dusted after rains, C is dusted once each week, and D is drifting once each week. I'm not actually sure what drifting is, to be honest. I need to read up on my agricultural lingo. And E is the not dusted. So E is just sort of the control, as if no treatment is applied. So here, we actually do have a Latin square. So if we look at the data, we have golden.Latin, and it's going to look like this. So in R, so what we have here is we have our treatment factor, we have our yield, we have our row, and our column. Now, the first thing we need to do is to make sure that R knows that the row and the column are in fact categorical random variables. In this case, because they actually correspond to rows ordered one after the next, we can treat them as ordinal random variables. So I'm going to say as.ordered, and we are going to say that, oh, not this, we need for the row, and no, I'm doing it backwards. Golden.Latin $row is going to be ordered. So this is just telling R that these numbers 1 through 5 are not literally the numbers 1 through 5, but instead ordered factors with the levels 1, 2, 3, 4, 5. Otherwise, the degrees of freedom will be all wrong in this case. And I wonder if there's an easy way. I'm not quite sure. If we were actually to, we could actually recreate this table. Yeah, actually, we can do that, right? We can just say, just to show you what the Latin square would look like, I can use the matrix command and apply that to our treatment column and say 5 by 5, and it should do column fills first. So this actually should work. Yeah. So this is what our Latin square is going to look like here. And if we stare at it, we should hopefully, unless there's some major error, only see one copy of A, B, C, D, and E in each row and in each column. And note that, again, the entire sample size is only 25, being 5 squared. So in this case, if we want to fit a model, we can use the AOV function, and we fit it really just as we would before, except that my, there it is, yield has fallen off the top of the screen. So what I can say is that the yield is going to be a function of the treatment, the row, and the column, and the data set we're going to consider is this golden.Latin. And what do we do when what do we get when we look at our ANOVA table? Well, what we get is something, well, quite neat. What we see is, well, the treatment, it's very significant F-test. So that's good. That means that at least one of our treatments is performing differently than the others. We don't know which one yet. That's for the Posthoc test. But we also actually see a slightly significant result for the row and a very not significant result for the column. Again, we do have to consider the idea of multiple testing. So this first p-value for the treatment is extremely small, even if we were to do like a Bonferroni correction. The row one is still small enough that I think it's worth investigating. And then the column one is definitely not significant by any means. So, okay, let's look a little bit more into that. Well, there's a couple things we can do. I guess the most sensible one would be to say, do Tukey HSD, apply it to MD. It's going to do a Tukey test for everything, so we're going to get a ton of output. We want to ignore the column one, even though there are no significant p-values here. You have to be careful because sometimes you might see a significant p-value here, and it would be erroneous because the column factor is not significant at all. When we look at the row, we did see a small significance in the F-test, and sure enough, when we look a little bit closer, we see a very significant p-value after adjusting for multiple testing between rows 1 and 4. So that's quite interesting. And then this one is again, not a little bit above that magical 5% threshold that Fisher said once, and now everybody treats as gospel. But at least 1 in 5, we say, okay, there might be a significant difference between 1 and 5. It's kind of close. The rest of them do not look very significantly different at all. So it's kind of hinting that, well, maybe something's happening as we go from row 1 all the way up to rows 4 and 5 as we move through the rows. But that's something that I think we get to look at a little bit later. More interestingly would be to look at the treatment, because the treatment is really where we saw a very strong p-value, and we can look to see where the significant differences lie. So A and C is very different, and C is giving a better performance or a better yield than A, significantly stronger. Here, C is giving a significantly stronger performance than B. We see that D is giving a significantly weaker, see the negative sign here, a weaker performance than C. And lastly, we see that E is also much weaker as a -8 than C. So you always have to remember which one's being subtracted from which. E minus C is negative means that C is actually doing better yield-wise or getting a larger response than E. In this case, the response is the yield, which means that our fungicide must be working better because we're getting more wheat crop out at the end of the day. So from staring at this, the obvious thing is that, C seems to be the best. And this is dusted once each week. So not considering, I guess, the rains or whatever drifting is, it just is kind of dust every week. And you get a better wheat crop out, apparently. At least you get more yield. And hopefully the fungicide washes off when you process it, because you probably don't want to eat that. But I'm not actually sure what the fungicide was that they were dusting with in this example. So maybe it's safe enough. Regardless, that's how we can go about and study this. And it is interesting, again, to note that here there actually was a significant row effect, or a mildly significant row effect, and a not very significant column effect. And if you actually go back to the textbook, which I have quoted in my notes, the 1957 textbook by Golden, Methods of Statistical, or here it's 52, but there I had 57 for some reason. It must be a different edition. Methods of Statistical Analysis. He basically says that the shape of the plot is what matters. They were long and narrow. So I guess long, narrow plots. Hence, he says the columns are narrow strips running the length of the rectangular area. Under these conditions, the Latin square may have little advantage on the average over the randomized block plan. So again, it's a natural thing to try, but I guess in this case, because of the shape of the plot, right? Square doesn't necessarily mean square. I guess if we actually went back to his field in the 50s or whenever this experiment was done, each of those squares was not so much a square, but a long, thin rectangle. But the Latin square design is still valid, even though the author here claims that you might just want to use some type of randomized block plan instead of the complete or proper, say, Latin square design. So that's more or less it. There's really not much more to it. It is worth always looking at the degrees of freedom, because here you can see it's K minus 1, K minus 1, K minus 1, and K minus what? K minus 3 times K minus 1, right? No, K minus 2 times K minus 1. 3 times 4. Yeah, 3 times 4 is 12. K minus 2, K minus 1. Yeah, it becomes K minus 3 if it was a Greco-Latin square, and then there'd be an extra treatment row somewhere in here as well. Right, so that's, again, that's basically the whole thing. It's always good to look at the degrees of freedom because it lets you know that you're doing everything correctly. If, for example, I forgot to tell R that these are ordinal variables, then we would run into some trouble. and it would, or categorical or ordinal variables, it would give me 1 degree of freedom and not 4, and we'd know that we were doing something wrong. So that's always a good thing to be aware of. Otherwise, that's the whole example. There's a lot of other places, though, where Latin squares show up that aren't explicitly fields. So what I wanted to take, I guess, 5 minutes just to say is that I actually used a Latin square 2 years ago now in the summer of 2019 to collect some speech data. So yeah, basically, I wanted to analyze some human speech. So I got my handy little audio recorder and went around and recorded people saying words. I had 12 words in the study. We can look at the data output here in terms of what are called log periodograms. That's basically just like a intensity of the signal at different frequencies. So it's like the intensity after you transform into from the time, the temporal to the frequency domain. The details are not important for this course. The point is that if I have 12 words and I want my subjects to say them multiple times, what's the best way to collect that data? Well, I could have a subject just say the first word 12 times, then the next word 12 times, then the next. But there could be subtle changes while the subject is speaking into the microphone. There could be background noises, because I'm just doing this like in my office. Someone could come down the hallway with a noisy cart, make some noise, corrupt the data. You could also have the fact that as we move through the experiment, or the data collection, I should say, the subject might get kind of tired and be like, you know what, this is super annoying after saying 100+ words. I'm getting kind of bored. I'm not really trying too hard. Maybe the pronunciation or the quality of the recording changes. So to account for all of that, what we did was we collected the data using a Latin square design. So each of the 12 words was read in some sense. Each row contained each of the 12 words once, and there were 12 rows. And every time the order was, I guess, something was randomized in the sense of a Latin square. So what that means is that if something changes as we move through the experiment, like there's background noise, like the speaker's a little bit more tired, we can account for that, and we can then see that within the data. Luckily, in this case, the data was pretty clean, but we can still use the row and column means to kind of clean up the data a bit before trying to analyze the speech sounds themselves. Speaking of speech, throat's getting a little dry. But that's just an example of how you can use the Latin square design for data collection and have a more clever and experimentally robust way of getting your data, right? Because ultimately we need to make sure that, we don't have any other confounding factors jumping in. So this gets back to the very first thing I think I said in the course, which is you got to randomize everything. So you take your Latin square, and in some sense, it kind of acts like a randomization. It will allow all the different factors or the different treatments to appear in different places throughout the design, whether that's spatially, like for an agricultural data, or whether it's temporally, like it was when I was having subjects read words or speak words into this microphone. And ultimately, that idea of randomization is really important. And I should say that you can find tables of Latin squares. So if you have an experiment that's like an 11 by 11 or 15 by 15, well, 15 is going to be weird because it's a composite number, but let's say 16 by 16 Latin square, you don't have to create it yourself. There's R packages that will generate the Latin square for you. There's also, I think in the textbook by Wu and Hamada, they actually have Latin squares in the back of the book. And what you can do is you can take your Latin square and you can randomize the column or the rows and randomize the columns. That is, you can do random column swaps and random row swaps, and you still have an equivalent Latin square. But by randomizing it, again, you're adding more randomization and you're making sure that you randomize your experiment as much as possible to control for other factors that may try to influence or confound what you're actually trying to test. So with that little rant about the Latin square, it's a pretty neat thing. I kind of like it. I was happy to figure out a way to actually use it outside of, say, walking around in a field, which I don't really particularly want to do. But yeah, I hope that that was interesting for all of you. And we're going to pick up again in the next lecture, and we're going to talk about even more types of multi-factor experiments, including the balanced incomplete block design. What happens when you can't test every treatment within every block? We'll also talk about the split plot design, which gets into the idea of how do we randomize? What if we can't completely randomize all of our treatments, and how does that affect the outcome? Because sometimes you can't randomize everything like you would like to, and you have to analyze that data very carefully in that case. But we'll talk about that in the next lecture, so look forward to seeing you there.